Hello, this is MAT221 Calculus 1. This is Mrs. Johnson. We're in section 5.1 talking about area underneath the curve and how we use area to approximate the accumulated change of the antiderivative. We talked about the LRam, the RRam, and the MRam here. This was the MRam, which is the midpoint rectangular approximation method. And the approximate area we got was 6.625. In this example, there were only 4 subintervals. As you could tell, we only drew 4 rectangles. So what Newton and Leibniz said is, well, as the number of rectangles increase, or the number of subintervals, in other words, how often I measure, in this case we measured every 1 unit, so we had 4 different units of 1. But as the number of rectangles increase, the number of subintervals increase, our accuracy will also increase. So with 8 subintervals, I would do something like this. I would say, okay, if I have 4 units here, but I'm going to have 8 subintervals, so if I take this amount, which is 4 units, and divide by 8, I'm going to then measure my width of each rectangle will be now half of a unit. So I'm going to find the value of the function at 0.25, then 0.75, and so forth. Now notice, which of the 3 rams did I use here? I used an MRam where the middle of the interval is being hit. The rectangle is hitting at the midpoint of the rectangle, not on either edge. So notice this, we were doing this on our calculator, so we'd say, well, if I have a 1/2 of a unit here as my width, I'm going to go in the middle of that, which is at 0.25. Then here, the middle of this is going to be at 0.75. Then the middle of this is going to be 1.25. And the middle of this will be at 1.75, and so forth. That's where I got these values from. And then I put them back into the original equation to find what the value of V was at each one of those values. So then I added up all my lengths here. So I'd say this is length of 1.00781. Then this length is 1.707031. And the length excuse me, of this rectangle was 1.95, and so forth. But if you notice, when I do length times width, these are just the lengths of all the rectangles. I have to multiply by the width of each rectangle, which in this case was constant. Each rectangle had a width of 0.5. So when I multiply those together, I get 6.65624. So here's my approximate area. Notice we got a lot more accurate here because the empty spaces above and below are getting smaller and smaller. The more rectangles, the more accurate my estimate would be. The actual answer in this case, by the way, is 6.6 repeating, or 6 2/3. So we are darn close to the actual area underneath the curve by just drawing 8 rectangles. So let's look at another curve. If I said to you y equals x squared from 0 to 1, and if I wanted to know this region S, this area underneath the curve between the curve and the x-axis, which is going to represent the accumulated amount of change in the antiderivative curve over that same interval. Now, I could use a left endpoint and a right endpoint, and you would notice in this case, the left endpoint, or the LRam, would be an underestimate of the area underneath the curve. I would add all of these rectangles areas up. Or I could use an RRam. Notice this is an RRam. The right corner of each rectangle is hitting the curve. And you can definitely notice that this would be an overestimate. And of course I could average the two and get a pretty good estimate to the area underneath the curve. Or I could add rectangles. So notice what I did was I used Mathematica here to draw these rectangles. What about if I have 10 rectangles? This would be the right-hand approximation if I drew 10 rectangles. By the way, there's the notation for that. It would be this. Or if I drew 30 rectangles, this would be the approximation. Notice the more rectangles I draw, these all being right 10 rectangles, 30 rectangles, 50 rectangles. Notice I'm having a computer do this and I'm not doing this by hand. 10 rectangles, 30 rectangles, 50 rectangles, but these are LRams or left-handed rectangular approximation methods. These R's are all overestimates. The L's are all underestimates, but notice the more rectangles I get, the more accurate my actual area underneath the curve will be. So, of course, we were talking about Leibniz and Newton here. So what did they think of? They said, what about if I take the limit as the number of rectangles increases without bound? My accuracy will be very, very accurate. Or could we take the limit as the width of each rectangle gets closer and closer to 0, but doesn't reach 0? I still have a width of each rectangle. This is what their thinking was as we move forward. So when we're finding the LRam, the RRam, or the MRam, the width of the rectangle is determined by the length of the interval and how many rectangles we want to draw. This can be done by using this little formula. Delta t, or the width of each rectangle, is equal to the interval, whatever the interval is from A to B, subtract A from B, and then divide by n, the number of rectangles. So delta t is considered the subinterval or width of the rectangle, or in other words, how often we need to measure. Now I wanted to show you the actual notation here that was used by a German mathematician called Riemann. Riemann was doing a lot of the same things as Leibniz and Newton were doing, but he used this notation. He called them L sums or R sums instead of an LRam or an RRam. If you notice, what he did here was, if we look at the notation, this particular image on the left-hand side is an LRam. Notice the left corner of each rectangle is hitting the curve. And look at his notation. He said at time sub 0, where I start measuring, the length of that rectangle is f of t sub 0. And then the width is whatever delta t is, the distance between the two t values. And then the next rectangle, the length is equal to the value of the function at t1 multiplied by delta t, and so forth, until we got to over here. Then we would have this last rectangle is the value of the function 1 less than our value of b multiplied by delta t. This is actually confirmed when we were doing those first rectangles. You could notice that when we're drawing an LRam, we're touching the curve on the left side. So we use the very first value at A, then each subsequent value except for the one right before B, because notice we don't use B as the, right? We don't use this B value when we're talking about the left side of the rectangle. We're talking about the left side of the rectangle, so we use one right next to B, that value that's right next to our endpoint. This is called a Riemann sum, or the sum of all the rectangles if you add up length times width, length times width, length times width, to the last length times the last width. This is an R sum or an RRam. Notice when we do these, we don't use the value of the function at t sub 0. Notice there's no rectangle that's drawn there. With the L sum we do, but with the right sum we move 1 over. So we start here at t sub 1, and then we draw it so that the rectangle is drawn so that the right edge hits the curve. So the length of our first rectangle is found by using our first T1 value, and then our T2 value, T3, T4, all the way up to T sub B, or T sub n, which is B. So notice with an LRam, we use the first value, the first input value, and all of them except for the last, so we use that. And for the RRAM, we use the last value and all of them except for the first input value. Here is our R sum, or our RRAM, for this particular function. Again, really cool notation here. This is all mathematical notation that Riemann used to give us an idea of what we are doing with this summing up the area underneath the curve. So if the velocity is positive, the total distance traveled is the area underneath that velocity curve. So here I drew about, I think it was about 20 rectangles. Here I drew about 50. Here I drew 100. And you can't even see, once we get pretty big, you can't even see the little lines between the rectangles anymore. The width of each rectangle is so small, it's hard to even capture it. So as the number of rectangles increases or the interval decreases, the interval in which we measure, the width of each rectangle goes closer and closer to 0, we get the actual area underneath the curve. All right, let's look at a couple examples here. With time t in seconds, the velocity of a bicycle is given by v of t equals 5t. How far did that bicycle travel in 3 seconds? Now be careful here. So many people want to jump right in and say 5 times 3, we went 15 feet. But that is not necessarily true. Let's look at this function. Let's look at the velocity function. The velocity function, v of t, is a linear function, v equals 5t. Looks something like this. And the actual area underneath this curve can be found by the equation of a rectangle, the equation of a triangle, because we have a triangular region. The base of this triangle is 3. The height of this triangle is equal to 15. So to find the area underneath the curve, we found the distance using this geometric figure, which in this case was a triangle. So we're going to use the area of a triangle instead of using our RAM methods, because this we can actually find the actual area of a geometric object. In this case, area equals 1/2 base times height, which is 1/2 times 3 seconds times 15 feet per second. Notice the output of the function at 3 was equal to 15 feet per second. And then we can see by our units, 1/2 times 3 times 15. This object has moved, the bike has moved 22.5 feet in those 3 seconds. Here we didn't have to use RAM methods because we had a geometric figure that we could easily find the area of. We will be learning how to find the exact area underneath a curve if we have an equation for a curve. Rectangular approximation methods are still useful for finding area underneath the curve if we don't have an equation. The calculator can do these rectangular approximations also. This is of some usefulness for us since we'll learn better methods to find the area underneath the curve, but we could always use our calculator to check. And when we're in class, I will be talking to you about how to do these things on your calculator. So right now, let's look at another example. Again, we don't have an actual formula for this function. All we have is some data. If we're given the data of the velocity of an object, we can use the data and its graph to give a good approximation of the distance that the object has covered or traveled on this given interval of 30 seconds. If we look at this, you can see that I drew an LRAM. So I drew this, I only have the data that we have above. So if I only have this data, this is all I have to work with.